The height of a helicopter in feet is given by the equation S of t equals 600t minus 2t cubed after t minutes. What is the total distance, keywords, traveled by the helicopter from 9 to 12 minutes? So last time we looked at displacement. Now we're going to look at total distance and see what the difference is. We're also going to look at the graph. So we're going to figure out the total distance traveled by this helicopter from 9 to 12 minutes. We're going to be doing the same steps we've been doing before with these types of questions, motion problems. The first step is to write out what is given algebraically. So here's the formula for the position of the helicopter. Remember that S of t denotes position, usually in these motion problems. Next, step 2 is to convert what is given verbally to algebraic expressions. So we've got two different times here. We've got t equals 9 and t equals 12, simply because it's going from 9 to 12 minutes, and we want to figure out how the total distance traveled between those two. Step 3 is to convert the verbally stated question into an algebraic expression. So I need to notate what's going on here. The total distance traveled is actually the integral of speed on the interval you're concerned about. So for here, we want to figure out the total distance traveled from 9 to 12. So those are going to be the limits of my integrand. And I'm doing this, I'm taking the integral of the speed function on that interval. So let's talk a little bit about that. One thing to note is that speed is the absolute value of velocity. Some of you might know that. Why is that? Well, velocity can be negative, but speed cannot. So for example, if your velocity is negative 7 feet per second, or feet per minute, whatever, then your speed would just be positive 7 feet per minute or feet per second, and so on and so forth. It's the same as if you're reversing your car. Your velocity would be negative because you're going backwards, but your speed would just show whatever's on your speedometer. We might say you're backing up at 15 miles per hour or kilometers per hour or whatever. So that's very important. Do not forget that when differentiating between speed and velocity, which illustrates furthermore, when you're talking about displacement, you just do change in y, right? We did that in the previous example. But with speed, it's more complicated. You have to find the integral of the absolute value of velocity. In other words, the integral of speed on that interval. So let's go ahead and do that. Now again, we've been hammering really on this concept of mapping out the difference between displacement, the difference between position, velocity, acceleration. So I want to show you that right now. As we do this more and more, again, like I said, it's going to be more clear to you as far as how these relate to each other. So for step 4, we want to map out the relationship between position, velocity, and acceleration. So a couple things to note here is that there's two ways to think about this. One is based solely on the position equation. So when finding total distance, you actually have to find the derivative of position, which is the same as velocity, take the absolute value of that, and then integrate it on that interval. So again, it's definitely more involved than just displacement. You could also just see it as the integral of the absolute value of velocity, which is the integral of speed. So next we have the actual speed function. So this is actually what you're going to find before you integrate. And again, it's just the absolute value of the derivative position. An easier way to notate that is just the absolute value of velocity, since velocity is the derivative position. And then we actually have the derivative of speed, or the instantaneous rate of change of speed, which is actually a form of acceleration, but it's different than the derivative of straight velocity. And you can see that because we have absolute value bars. Those are going to be slightly different. We'll talk about that later in another motion problem, but for right now we're just focused on total distance, so basically this column. Okay, let's take a look at step 5. Okay, step 5 is to solve the problem using either initial value or derivative procedures. So in this case, we're doing both. We're going to be both taking the derivative and integrating. And when we integrate, we find the definite integral. So remember, velocity is the derivative of position, and why are we finding velocity? To find total distance, you actually have to take the derivative first and then reintegrate. It's kind of weird. So velocity is going to be the derivative of our original equation. By the way, this is our first example for motion problems where we're actually taking the derivative. But anyways, so our velocity function based on this position function is going to be 600 minus 6t squared. That will be using the power rule. Then from there, we can now, of course, take the absolute value of this, and we will then integrate that. So this is what the absolute value of the velocity looks like. So this right here is, again, is actually your speed function. I'll go ahead and notate that. So whenever you have a velocity function inside the absolute value bars, that indicates speed. Now, you can't just, so many of my students say, okay, there's a negative here, I need to make it positive. No, that's not the way it works. We can talk about that some other lesson, but you just want to leave this as it is and then integrate on that interval. So we've done a lesson in this class before on integrating absolute value functions. And of course you need to know that in order to integrate this function before you can plug in the 12 and the 9 to the definite integral of this. So another thing my students mention is, why not just plug in these numbers into the original? Well, these absolute value bars are what makes the difference. And when we get a look at these graphs, you'll see why there's a difference between displacement and total distance traveled. So in order to find the definite integral of an absolute value function, you want to figure out where it crosses the x-axis. So you set it equal to 0. You find the zeros of the function. In this particular case, and so actually you're taking the function inside the absolute value bars. You don't have to include the absolute value bars, but we'll see how this works in a second. So when you solve for t, you can pull a 6 out. You get 100 minus t squared. You're going to get t equals 10, negative 10 and 0. Negative 10 is not the solution. So either 0 or 10. So it crosses at those two places. So let me see if I can zoom out here so you can see this. Okay, yep. Okay, so there we go. You got to choose your interval. Your definite integral interval is from 9 to 12, right? And so this is the only number that's in between those two numbers. So you want to figure out, you're going to set two intervals up based on this number where the absolute value function crosses the t-axis or the x-axis. Plug in some test values and see what happens. So when you plug in 9.5, which is in between 9 and 10, you get 58.5. That tells you that the velocity is positive in between 9 and 10 minutes of this helicopter flying, and therefore it's above the t-axis or the x-axis. Now from 10 to 12, which is your other interval, if you plug in 11, you get a negative number back. And again, I'm actually just plugging those into my velocity function. I didn't have space here to do that in the chart, but that's where we're plugging it in. So if you plug in 11 right here, you're going to get that negative 126. So that tells you the velocity is negative between 10 and 12. And just remember that basically when you're doing converting velocity to speed, you're taking anything that's below the t-axis or x-axis. So in this case, the interval 10 to 12, you're taking whatever that graph is that's below the t-axis and flipping it up, making it positive. And that will actually give you your speed function, because it's an absolute value, right? And anything that's below the t-axis or the x-axis, you flip up. And when we look at the graph, it's going to be very clear as far as what's going on. Okay, so I decided to go ahead and show you this graph since I've been talking about it so much, then we'll finish the problem. Here's the velocity function. We can see that the velocity continually decreases throughout this time interval from 0 to 16 or however far you want to go. Notice what happens at 10. The velocity becomes negative. So that's the point at which the helicopter starts to actually go down, right? So the helicopter is rising from 0 to 10 and then starts falling back down at 10. So if we're looking at the speed function, since the helicopter is falling right here, its velocity is negative. For speed, that doesn't matter, right? For example, right here, its velocity is around negative 400. Well, its speed would just be positive 400, right? Because speed is always positive. So you're just taking this piece of the graph and you're flipping it up. And so when you do that, this is what this speed function looks like. It ensures that you never have a negative speed. And any velocity it's negative, you make positive. Now you can have zero speed right here, but you cannot have a negative speed. So I wanted to be clear about that so you can kind of see what's going on with the helicopter. And that way, it gives you more clarity as we continue to finish the problem. Okay, so since it's positive from 9 to 10, we don't do anything to the velocity function. However, since it's negative from 10 to 12, if we take that piece that was below the t-axis and multiply it by negative 1, it will flip that part of the graph up and make it positive. So this is going to become negative 600 plus 6t squared. and I don't want to show everything from 10 to 12 that you plug in as positive. We find these two separate integrals, and again, this is the process for finding the integral of an absolute value function, is to split it up on that interval. I want to be clear about that because that can be confusing for some students. So here's our two integrals. Change the signs and everything. We're going to be using the reverse power rule. You can flip this around right here to make it more easy to integrate, I guess, or just looks better. So the first integral is 600t minus 2t cubed using the reverse power rule, going from 9 to 10, and the second one is 2t cubed minus 600t, going from 10 to 12. We plug in our intervals, and then we solve that. This is actually one big thing right here, just to give it enough space. This is just arithmetic, and we get 314. And of course, to top it off, we want to answer this verbally. Okay, so verbally, the helicopter travels a total distance of 314 feet from time t equals 9 to t equals 12. Now, I don't know if you remember or not, but its displacement was negative 198, meaning it fell 198 feet. So how can it be that it traveled 314 feet total? Well, I want to show you kind of what that looks like. So I'm going to draw a picture to illustrate this. Okay, so what happens is the helicopter takes off and it just rises straight up. This is all about vertical positioning, right? So at t equals 9, it actually hasn't reached its pinnacle at t equals 10, right? It's still climbing. So it travels some distance from 9 to 10 up, right? And we might figure that out later in one of the problems in the future. And then at t equals 10, it actually starts falling, as we saw in the velocity graph. And it falls below its position at t equals 9 and actually falls. So this distance right here between this red mark and this red mark is a drop of negative 198, which we found in the displacement question. However, its total distance includes this part where it went up and then back down again before dropping down to t equals 12. This is why the total distance is 314 feet, because it includes all of that travel between the 9 and the 12, going both up and back down again. So that's it for the total distance problem of the helicopter. If you have any other questions about this, let me know.